Now we are going to learn about refinements for Kkd-trees so as to get rid of the limitations which we saw earlier, right? So there is a very basic idea here, which is that of using splits which are not going to be orthogonal to coordinate axes, right? So in other words, so the basic construction would be the following. So if we are in dimension d, consider the unit sphere s to the d minus 1. Now pick uniformly at random a direction on this sphere, right? And use this direction, let's call it u, and use this direction to run the projection. So in other words, so this is what you see here. So we picked a random direction, this one, which is neither x nor y. So we project all points onto this direction, and now we compute the median, right? So the median is going to be this point here. We have, so 4 points to the left, 3 points to the right. So we have an even number of points. And so, of course, one of the two subsets has a number of points which is the size of the other one, minus 1. But nevertheless, so this is a median. And now we are going to split, actually, the wall space using a hyperplane orthogonal to the random direction and running through the median, right? And so if you do so, so here is what the resulting tree looks like. So in a Kkd tree, of course, we have hyperplanes orthogonal to axes to run the partition. And so in a random projection tree or random partition tree, as you can see, so we have splits which now are at random. Right? And so, of course, one complication is that so the cells in a Kkd tree are boxes, right? Hyperrectangles. And now in a RP tree, so things are much more complicated. But still, the good thing is that we retain the property which tells us that this is a balanced binary search tree. Okay. And so, interestingly, this business about random directions and also this idea of using overlapping splits, as I mentioned at the end of the previous lecture, so this is going to be instrumental in improving all search algorithms, right? So again, the simple improvements we are going to use are overlap, allow some mild overlap between cells so as to recover the nearest neighbor even though it is not sitting in the cell which contains the query point, okay? Use randomization to actually build these partitions, and in particular, in fact, what may be done too is to build not a single actually RP tree, but you can build as many as you wish, right? Because whenever you are going to, so this is a randomized construction. So randomized meaning that if you run the same construction twice, you will get two different data structures, right? So hopefully they will yield the same nearest neighbors if you actually run such a query. But in fact, in general, the answer is going to be no. So you may have different solutions upon querying two different trees, except that this is going to happen with a small probability. Right? Okay. So, so here is, again, the pseudocode for building a random partition tree. So we are assuming, as previously, that we have a bound n0 on the maximum size for a point set stored in a leaf. And so now there is randomization actually in the most general setting for random projection trees. So we have two randomizations, in fact. So there is the first one, pick uniformly at random from the unit sphere, right? So project points onto this sphere. And then what you can do is to split at the median, as we did earlier. Or I'm also now introducing this, we call this a jitter, this perturbation on the median. Instead of picking the median exactly at 1/2, so you may also slightly shift it to the left or to the right. And so to do this, you can take a real number uniformly at random, let's say in some interval centered on the median, for example, 1, 4, 3, 4, 3/4. And then in fact, what you are going to do is to define a rule. So so you project now your points on your random direction, right? And V, so it's going to be the beta fractile point of the projection of S onto this random direction. And essentially, so you are going to say that a point X is routed or sent to the left subtree if in projection along the U direction, in fact, you get a number which is less than beta, right? And it's going to be routed into the right subtree otherwise. And now you call the recursion, namely you build the left subtree with all the points in the current subset such that the rule tells you that such a point goes to the left subtree, and likewise for the right subtree. Right? So again, here in this pseudocode, so randomization occurs twice. First of all, in picking this random direction, and secondly, in actually splitting not exactly at the median, but at the number beta, which actually is not too far from the median. And so in fact, with these two refinements, so we can play a number of games. And so this is where I'm going to introduce actually so-called split trees and their variants. So again, so if I'm splitting exactly at the median on the random direction U, I'm defining, well, a randomized partition tree, right? And so here, this is with an exact split. If I'm splitting on the direction U at a number beta between, let's say, 1/4 and 3/4, I'm defining a randomized partition tree with a perturbed split, okay? And so here, the good thing is still that of course, so here I'm slightly disbalancing the two subtrees because the left subtree will get less than the right subtree. But because, in fact, beta is bounded, bounded away from 0 and bounded away from 1, I'm sure that in a logarithmic number of steps, I'll be done anyway. And finally, there is this interesting idea, which is the following one. So now let's consider some number alpha, for example, 5%, 0.05. And so instead of having such a split here, be it exact or perturbed, so let's assume that we are going to make a split, but in fact the domains associated to the left subtree and the right subtree, they will overlap, right? So this is exactly what you can see here. So the median is here, and so in the left subtree, I'm going to store all points such that in projection, these points project at 1/2, well, they project to the left of the median plus alpha, right? And likewise, in the right subtree, I'm going to store all points such that in projection, in fact, they project at a value which is larger than the median minus alpha. And of course, these two intervals here, from 0 to the cut for the left subtree and from the cut to 1 for the right subtree, they have equal length, which is in fact 1/2 plus alpha. Okay, so here, so this is quite subtle, well, and in fact, so it allows us to define what is known as split trees. So, and in fact, split trees, we have two options. So in regular split trees, what we are doing, so look, we are going to, when you are going to build the tree, so again, the domains associated with the right subtree and the left subtree, they are going to overlap. For example, here they are overlapping on 2 fingers, right? Which means that some points are going to be stored twice. All the points which are sitting between, in fact, so look, all the points which are sitting here, they are going to be stored twice, on the left subtree and on the right subtree. So let me try to clarify this. So, right? If we have a random direction, so let's say this is the unit sphere, right? We pick a random direction U. We project all points. Okay, we project all points onto. Oh, I could also pick points. We pick all points. We project all points here. Okay, so the median is going to be this one, and so in the exact split paradigm, in fact, I'm splitting using this hyperplane, right? Okay. But now, if I'm allowing some overlap between the cells of some quantity alpha, maybe alpha equals this much, right? Okay. So the left subtree, okay, let's say this is the right subtree, sorry. The right subtree, in fact, is going to accommodate all points which project, in fact, up to the median minus alpha. Okay? So this is going to be for the right subtree, and likewise, the left subtree is going to accommodate all points, right? So here there is none, in fact, which projects all the way to the median plus alpha. So sorry, so here the two lengths should be equal. But this is the idea. So in doing so, so as you can see, for example, this guy here, this point, it belongs to the right subtree, but it also belongs to the left subtree. So it means that, in fact, all points which are falling into this overlapping zone, they are going to be stored twice, possibly into the left subtree and the right subtree. Right? And so why is this interesting? Because, again, if we want to run the Defetis search, if you remember, what was the main problem in using the Defetis search? The problem was that sometimes, so we had a query point which was sitting here, Q, in the left subtree, but in fact the nearest neighbor was in fact located here, right? So this was NNQ, right? It was sitting on the other side of the fence. So now, if we say that the left subtree also accommodates, so let me use the same color. So the left subtree is in green here. If we are saying that the left subtree also accommodates a portion of the neighboring region, so then of course, and if this, because this point is also stored in the left subtree, so I'll be finding it. Right? So, so this is in fact the notion of regular split tree. We have overlapping cells which yield redundant storage of points. And of course, there is a refinement of this, or a dual idea. So one may say the following. Well, in defining actually regular split trees, so we are creating redundancy in storing the points, but then when we are running the search, we are traveling down the tree in the Defetis side, right? So what about doing the opposite? Namely, so let's build a tree without any overlap, but then when running the query, let's route the query actually using this overlap. You see the difference? So in fact, it's essentially the same, except that we are using the overlap between regions, not when building the tree, but when running the query. And so, so from this discussion, let me recap by saying that we'll be analyzing the sequel 3 types of trees. So the random projection trees, where we have a perturbed split here, like this one, right? So without any redundancy in the storage, and when routing a query using the Defetis search, we'll be descending down the tree once, and of course we'll possibly get fooled if this situation happens, but because now we are slightly shifting the median using some value beta, this is expected to happen less often, right? And then we have these regular and virtual split trees where, again, for the regular split trees, so in fact the redundancy is used when building the tree and not when running the query. And for virtual split trees, it's the opposite. We are using actually a median split, right? But when routing the query, right? So if we are querying for a point which is falling here, so we'll query it. We'll run the query in the right subtree, but we'll also run the query in the left subtree. Is it clear for everyone? The distinction. So you have, it's very simple, right? So you have a direction, you have the median, and apart from the median, you have a band. And so to the left of the band, so the points go into the right subtree, and to the right of the band, the points go into the left subtree. And so this redundancy may be used in 2 different ways, either by storing the points twice, which is going to yield a super linear storage, because these points in this band, some of them will be stored twice, or at the query time, which means that in doing so, you will have exactly a linear size data structure, but just a number of queries will be routed twice, and so the search is going to be slightly more costly. So what I would like to do now is to try to provide some analysis and some guarantees on these data structures to convince you that, in fact, they are a good choice. So here I'm missing a letter E, so the tree depths. So first of all, so let's analyze the tree depths, right? So because we have some redundancy for regular spill trees, and so is it clear that, in fact, this does not yield too much when talking about the depth of the tree? So, in fact, the observation is the following. So, the number of nodes transmitted to a zone decreases by a factor at least this much, right? So, when we are building regular spill trees, so yeah, so because alpha is, if we bound alpha away from 0 and from 1, so we are transmitting at least beta to one zone, right? And so if we are assuming that we have up to n node points in a leaf, it means that, okay, so so now, so this is just a recursion, right? So the depth L of the tree satisfies that, okay, so you, so this is a geometric, a so-called geometric progression, right? So if you are sitting at depth L in the tree, so you have exactly beta L n points, and you want this to be less than n 0, right? And from this you take the logarithms and you get that the depth of the tree is exactly the logarithm in base 1 over beta of the ratio n divided by n naught, okay? And now because this is a binary tree, so you get that the tree size is exactly the number of nodes, is n0 2 to the L, namely n0 raised to the power to the power of the depth, namely this formula. And so, for example, if you are building regular spill trees with alpha equal 0.05, right? So you get that your data structure now is using a superlinear storage, namely n to the 1.15. So, in fact, as you can see, this redundancy, you slightly pay it. If you want to enlarge this stripe here around the median up to 0.1, 10%, right, of the range occupied by the values in projection along the random direction u, so then you have that your overall size is going to be 1.35, n to the 1.35. So this is getting to be quite quite significant, right? Especially if you have a very large database. So now, of course, it depends on how many points you have. Okay. So these spill trees, in fact, what one is doing, you are compromising the storage versus the quality of the neighbors which are returned, right? But of course, one should still be aware of the fact that even if you are overlapping, using overlapping regions, so the search may fail, right? Because if you are, for example, in this situation, if you have many points here, many points there, if the median is here, and if your query point, as you can see, your query point here is going to be stored in the right subtree only, whereas the nearest neighbor actually is located beyond the overlapping slab, namely, let's assume in projection it is here. So as you can see here, if you travel down the tree defeticile into the right subtree, so you will never find this point. But again, so in other words, so this problem which I recall here of having a neighbor which is sitting on the wrong side of the boundary, of course, may still happen with with spill tree, except that even if you have shifted the boundary, if your point is to the right of the shifted boundary, so you're not going to find it. So that's still a limitation. So nevertheless, so what we can try to do is to try to fully understand, to try to write theorems, to analyze the probability with which the search will fail. And so in fact, I'll essentially state a number of theorems. So on the slides you have the proofs are quite simple, actually, elementary. And so on the slide, so I'll give you the main steps and also the references for the paper within which these results are proved. And so what I'll be calling ER, like error, is the following. So if we care for the nearest neighbor, so ER is the event the search does not return exactly P1, right? So the point with this subscript in parentheses so means that this is the point set upon sorting with respect to the query point, right? So in other words, if we have a point set, right? We have a query point Q, and so the nearest neighbor is going to be P1, and the second nearest neighbor is going to be P2, and the third nearest neighbor is going to be P3, and so on and so forth, right? So they are sorted by increasing distances, and the index is reflected by this, the position of a point from the database in the sorted sequence is reflected by its index. And so again, what is the, when are we making an error? If we want the nearest neighbor, the search does not return P1. And if we care for k nearest neighbors with k larger than 1, so then we face a failure when, in fact, we do not get, in fact, the set P1 to Pk. But in fact, some other point made it into this set of size k for some reason. Okay. So there, something extremely interesting has to be mentioned. And in fact, this is also related to a topic we'll discuss next time, which is measure concentration phenomena. So we have been talking about nearest neighbors, but do nearest neighbors make sense at all? So in other words, is it clear that caring for the first nearest neighbor makes sense? So another way to put it is the following. So there are possibly situations where indeed, it clearly makes sense to speak about the first nearest neighbors, but there are situations where it does not. And so let's inspect such situation. Here, if I'm sitting at Q, obviously P1, the distance to P1 is much smaller than the distance to P2 and so on and so forth. So we have a gap in terms of distances, right? So in this situation, on the other hand, it's not so clear. And in fact, the opposite holds. If we are sitting at Q, look, P1 is centered, P1 is here, the nearest neighbor. But if we call the distance maybe d, look, this guy is a distance d multiplied by 1 plus epsilon. Likewise for this one, etc. So in other words, if my point is a center of a ball next to which all the points are located, so in fact, speaking about the nearest neighbor does not make much sense, right? Because, okay, let me say it one more time. So here, if you are in this situation, for sure, you want the algorithm to return P1. But if you are in this situation, you'll probably be happy with P1 or this guy or this guy or this guy, because after all these points, they are essentially at the same distance. So in fact, mathematically, we would say that the problem is ill-conditioned. Like when you're solving a linear system, somehow, there is not a unique solution, right? So you cannot solve your linear system. Okay. And so there is an important function which is capturing this notion, and this function will be called phi in the sequel. So again, let's assume that we are sorting the point set P1 to Pn, the database, with respect to point Q. And now, if we care for the first nearest neighbor, let's compute the following. The sum of the ratios for all the points from 2 to n of, in fact, the distance to the nearest neighbor divided by the sum of the divided by distances to the remaining nearest neighbors. Right? And so, of course, there are some extreme cases which correspond to these figures here, right? If phi is equal to 0, it means that these denominators are large with respect to the numerator, meaning that P1, so here I'm missing parentheses, sorry, P1 is isolated from the rest of the crowd, and so in fact, in that case, because finding the exact nearest neighbor is easy, we expect the algorithm to find it, indeed. Now, in this situation, if phi is almost equal to 1, what does it mean? What does it mean? It means that, in fact, here for all the points, this ratio is almost equal to 1. In other words, all the points are essentially at the same distance as P1, has the exact nearest neighbor. And so in that case, when phi is equal to 1, the problem is ill-posed, right? So here I should be able to live with P2, P3, P4 because the distances are equivalent. Okay. And so, of course, now we have been discussing the failure probability. What about the failure probability, namely the fact that in running the algorithm, so we were not recovering the exact nearest neighbor. But in fact, in light of function phi, so what we would expect is the following. In fact, in using random projection trees and spill trees with a defeatist search, so what is expected is that the probability of success or failure should depend upon phi, right? In other words, if you are using this defeatist search strategy to run an NN query in an easy case, when phi is equal to 0, so then the probability of failure should depend upon phi and should be small, right? And of course, likewise, if phi is equal to 1. And so this is indeed the case, and this is what I'm going to show you. So this is quite interesting and quite important. So because I mentioned also these generalizations of function phi for cases where we are dealing with k-nearest neighbors, so I need to introduce two generalizations. So the first one is the function phi for a cell of the tree which is containing m points, right? So in that case, what we are doing, so this is essentially the function we had previously, namely we take the ratio of the distance to the nearest neighbor divided by the distances to the remaining sorted points in the cell of the tree, right? And now another generalization, which is what if we care for the k-nearest neighbors, because of course we want to find some kind of condition number to assess the easiness or difficulty of finding the k-nearest neighbors. So it's exactly the same. Namely, we take as a reference in fact, Q minus Pi, right? So it's it's exactly the generalization of the previous formula, except that here at the numerator, we are using the sum of distances to the k-nearest neighbors, and we normalize by the distances with the remaining points, namely those which are not among the k-nearest neighbors. Okay, so so now in order to present the theorems, which are precisely assessing the performances of the defeatist search using either random projection trees or regular spill trees or virtual spill trees, so we need some lemma. And in fact, so the lemma is about, in fact, let's assume that we have 3 points, right, such that, so the configuration is the following one. So let's assume that we have 3 points. Q, X, and Y. And so this is going to be Q, this is going to be X, and this is going to be Y. So we assume that the distance between Q and X is less than the distance between Q and Y. Okay. And so we'll be taking a random direction, as usual, U, on the unit sphere, U. We'll be projecting actually Y here, Y prime. We'll be projecting X here, X prime. And what we want to assess is, in fact, so the event which I call E here is that the projection of Y along U, namely Y prime, falls strictly in between the projection of Q on Y, so Q is here, the origin, Q equal Q prime, and X prime. So here it's not the case. Y prime does not fall, strictly speaking, in the interval defined by the projection of X and the projection of Y. Okay, so here, the event E is not occurring. So what I did a small application. So I'm also going to show you a piece of software which you may like. So where is it? So did you ever hear about this little application, Dr. Geo? In fact, this is, so of course, if you're using, by the way, let me show you another one also before that. So, which I think you should know for sure. So, IPE, so this is like an editor within which actually you can type your LaTeX formulas, right? For example, fraction of X divided by Y, and so on and so forth. And so, in fact, here, so look, so this is you can store PDF files which contain LaTeX formulas, and in fact it also contains application to draw Delaunay triangulations for Voronoi diagrams. So this is a neat application. So if you want to, if you are picky on your drawings, for example, you have magnets like now in a number of things, right? So for example, if you are using this magnet, so you will make sure that here you snap your point exactly where you want, and so this is perfectly neat PostScript. So containing LaTeX formulas, and so IP is quite convenient. So I put the web address from which you can download IP. So the problem with IP and all these softwares is that when you do a formula, it is static. So with Dr. Geo, so now look at this. So I'm not going to, it would take 2 minutes to do this. This is exactly the configuration which I displayed here. So what I did is the following. I define a point Q, I define X, I define Y. And then I define this random direction U, right? And I define Y prime as the intersection between the line passing through direction U. And Y prime is a projection of Y onto this line, and likewise X prime is a projection of X onto this line. And so now the beautiful thing here is that I can move things around. So look, and so because each formula, each construction is dynamic actually. And so now, if you want to understand whether the formulas which we'll see in the lemmas are correct or not, or are tight or not, whether the upper bounds are realized, you can pick specific configurations for Y, X, and try to see what is the probability. So here we are in 2D, but for U it's a random direction on the unit circle, so it takes value between 0 and 2 pi, right? And so now we can try to understand what is the probability to have the event E occur, namely to have Y prime contained between X prime and Q. So look here, so now the event is occurring, right? So if I'm picking this random direction U, so in projection, in fact, Y prime here is contained in the line segment Q prime, X prime, right? And this is going to be so all the way to this random direction here, right? And then now it disappears again. So the property vanishes again, right? So you see, so this is the event E I was talking about is precisely this one. So what we see here, so we have a point Y whose distance to Q is larger than the distance between X and Q, yet in projection along a random direction U, Y prime falls in the interval Q X prime, okay? And so of course this is a critical property for the correctness of my algorithm. Why? Because the algorithm is splitting along the random directions. But look here, what's going to happen here? What's going to happen? Well, if my query point is Q, obviously by construction, I'm assuming that the distance between Q and X is less than the distance between Q and Y. So in fact, in listing the nearest neighbors of Q, I should find X before finding Y, right? Except that if I have picked this random direction, so look, I picked a random direction and I'm projecting things actually on this direction. And so what's going to happen in computing the median or the jittered, the shifted median? In fact, if I split the direction here, so look, in fact, I'm going to put in the same cell, namely in the cell with maybe, or if I was to split with this hyperplane here, right? So I can maybe put a point. Yeah, okay. If I was to split using this, now I need to define a line with 2 points. Line with 2 points. This guy maybe, yeah. What is this? Line defined by 2 points. Yeah, this point and that point. Yeah, okay. If I was to split using this line, look, I would find in the left subtree actually a Y, but the nearest neighbor of Q, which is X, would be in the right subtree. So typically this random direction, let me remove the line, yes. Let me remove the point, yes. Yes, okay. So in other words, no, move. So random directions such that Y, which is not the nearest neighbor of Q, projects between Q and X prime are the dangerous directions, right? Which are going to to actually jeopardize the algorithm, and which are going to be such that in some cases the nearest neighbor search may fail. Okay. So in fact, so we have some simple lemmas here. So this one is a bit so requires some calculations, but essentially we define a collinearity index between the query point x and y, which is this much. And then we have the following lemma, which say that if you pick 3 points with this property, as I said, the probability over random directions u to observe the event E is exactly the following. Right? So this is the probability to have y projected between q and x, even though the distance between q and y is larger than the distance between q and x. Right? And then you have two simple bounds, which use properties of the arc sign, which I'm stating here. Okay. Okay, so this was the demo. And so here from the slides, you'll be able to grab IPE and Dr. Geo. Okay. So now, so let's, again, so I don't have time to get into the details, but the proofs are pretty simple. So let's try to make sense out of the statements. So we consider a query point Q, a point set, a database of n points in R to the D, and a random direction. And so the first statement tells us that the expected fraction of the projected points falling between Q and P1 is at most 1/2 of this potential function phi which I introduced. So if you remember, phi is essentially 1/n times, in fact, the sum over all remaining points of the ratio distance Q to P1 divided by distance from Q to Pi. Okay, so in fact, so the proof is actually written here. So you care for the event Pi falls between Q and P1 in projection. So by the previous lemma here, you have this upper bound, right, which is written here. And then you just apply the linearity of expectations, and you end up with this quantity. So as you can see, so phi is indeed the function which gives you this probability. So now, more interesting is the following theorem. So we consider a point set, a subset S of the whole database, P, such that S contains the nearest neighbor of Q. And now, if U is chosen uniformly at random, then, and also if alpha is less than 0 and 1, so remember, alpha is the parameter which is governing the construction of spill trees, right? Actually, of regular spill trees and also of virtual spill trees. Then the probability that an alpha fraction of the projected points in S fall between Q and P1 is bounded by actually this quantity. So this is a function which I also define. It is phi. Sorry. So there is an extra phi here. It is a restriction. So this is the size of the point set, right? Phi of m in my previous notations. Phi of m, namely the point set falling in the leaf, which are in the node I'm currently considering, and then phi of q and p. So the proof is quite simple, also. And now let me make the main statements, which are about the performances of regular spill trees. So let me recap. So in a spill tree, so the storage is such that a point is possibly stored twice using the overlapping split with parameter alpha, right? And these trees, we have seen that they have a depth which is logarithmic in the number of nodes. And again, in a regular spill tree, so redundancy at the construction of the tree, but regular routing using the defective search. And so the theorem is the following one. So let's use beta equal 1/2 plus alpha. So then the probability to have the nearest neighbor returned by the defective search using a regular spill tree is actually bounded by this quantity, right? 1 divided by 2 alpha, and the sum over all levels of the tree of, in fact, function phi applied to all nodes of the tree. So remember that so we are starting with n nodes, right? The root of the tree is at depth 0, I is equal to 0, and it has n nodes, right? So here, if I is equal to 0, so here this is n, phi of n, q of p. So this, when I is equal to 0, this is standing for the root of the tree. So of course, the error we are talking about when we are running the defective search. So remember, we have a tree, right? So it's a binary tree, and so on and so forth. So if I'm routing my query, if I'm following this path, of course, so when am I going to fail? I'm going to fail when the query point is routed on one side of the tree, whereas x1, the nearest neighbor, is routed on the other side of the tree, right? Even though I'm using split trees, right? And so, in fact, the failure may happen here, may happen there, in fact, may happen at any level in the tree, whence actually this formula, right? And now, if you care for a particular level of the tree, namely at depth I, right? So what is the probability to have a failure at depth I? Well, it's the probability, again, to have Q and X1 and P1, the nearest neighbor, routed on different subtrees, right? And so at depth I, we have in our node exactly beta I n points, right? And so in fact, so the quantity we are adding up over all levels of the trees is exactly this one, right? Okay. And so if you do so, you end up with this quantity, which is, again, a bound, an upper bound on the failure of the search obtained by actually using union bound, namely by adding up the failure probabilities associated to, in fact, all the nodes which are visited upon routing the query in the regular split tree, right? So you get the whole idea, yeah? Hopefully. So now, so there is an equivalent statement for an equivalent statement for virtual split trees. So, so again, for virtual split trees, what's happening? So each point is stored in a single leaf with median splits, and the depth of the tree is still logarithmic. It's actually the same, right? But now the difference occurs at the routing stage because we have this parameter alpha, which is quantifying the overlap between regions, right? And so a point may be routed to two different subtrees. And so in this case, it turns out that in using beta equal 1/2, in fact, one can prove a theorem which has the same form as the previous one, namely the probability of the failure is in fact obeys the same bound here. In fact, the proof is essentially the same. And so this is quite satisfactory because, again, so now we are getting a behavior for our algorithm which depends on the intrinsic difficulty of the problem. So remember that function phi is coding the distribution of points, right? So it tells us whether we have a well-identified nearest neighbor or not, actually. So now, the third version of the tree, which is the random projection tree. So remember, let me recap again. So for a random projection tree, so one is doing the following. So we pick a random direction, we project onto it, and then instead of splitting at the median, we jitter, we perturb the median in some interval 1/2, 1/4, 3/4, right? And of course, this means that each point is stored in a single leaf, right? And to route the queries, so we are going to proceed like for regular split trees with defective style. We go all the way to the leaf containing the point, right? And so in that case, the bound is slightly different. So we don't have a sum of phi of the points. We have a sum of phi log phi, essentially. So the proof is a bit more complicated, but in spirit, as you can see, it is in the same vein, if I may say. So you're going to get a performance which depends upon the configuration of your point set. Okay. So, so this was a recap for, just to say that for split trees, whether we are talking about regular split trees or virtual split trees, so the bound is the same. So we have already seen this. So this was for finding nearest neighbors, so trying to avoid the separation. And here, this is an interesting example which shows us, so of course, so I've mentioned these three theorems for all the trees which are using these two tricks again, so the random, actually projecting along a random line, and for random partition trees actually replacing the median by a perturbed version of the median, right? So, so of course one may say, is it really mandatory to use this randomization? In other words, wouldn't it be possible to get the same behavior using Kkd-trees or something like that? And so here is an example where actually one sees that the answer is no. In fact, if you're using Kkd-trees, in fact, you may have a behavior which is completely different from that of random projection trees. And so the example is the following one. So we are going to build a database, a point set, such that, okay, the query point is at the origin, as usual. So x1, so here we are in 3D. So x1 is the all ones vector. So, okay, so let me show you the coordinate axis. So this is x, this is y, and this is z. Okay. So x1, it is a point having all its coordinates to 1. And then for x2, x3, and all the way to xn, we are going to do as follows. So to build such a point, so we pick a random direction, so from 1 to d. So maybe for x4, as you can see, I picked as direction x. And so we assign, so this point here in orange is a point on the coordinate axis such that it has a very large coordinate, m, and all the remaining coordinates to 0. And then what I'm doing, I'm replacing all these zeros by a uniform distribution in the square, actually 0, 1 to the d minus 1. So in other words, I want to find a point here which is sitting in a plane orthogonal to the x direction, and which in projection is going to be here next to the origin. Okay, so this is the way I'm going to build my database. I have x1, the nearest neighbor, and I have these remaining points which are each of them is sitting next to a coordinate axis with a version slightly perturbed, right? So of course, if we were to use a Kkd-tree to process this point set, what would happen? So, well, first of all, so the point set, of course, is such that the nearest neighbor of the query point q is x1, right? Because all the remaining points from x2 to n, in fact, they are far away. Now, if we were to build a Kkd-tree to store this point set, so what would happen? In fact, let's assume that we would need to pick a random direction, right? But a direction that would be a coordinate axis, right? So maybe we would pick, in fact, maybe we would pick x1, right? Okay, and then we would project all points to x1, right? All points on this coordinate axis. But in doing so, in fact, all the points which are not associated with x1 here, they would project actually in between q and the projection of x1, right? So look, for example, this point x3 here, if I was to project, x3 is here, if I was to project it here on the axis x1, it would be sitting here. Now, let's take this one. If I were to project this one onto the x-axis, so it would project maybe here, right? But of course, along the axis y here, z, sorry, I would also have a number of points that would project here. And so in this case, upon picking a random direction, which is a coordinate axis, the fraction of points falling in between q and x1 is in fact exactly this quantity. The expected number is 1 over n, the number of points, and all the points which are not along the axis which has been chosen, all these points, they are going to project between Q and X1. And so this fraction is 1 minus 1 over D. And so as you can see here, we have a large fraction of points which project between the query point and the nearest neighbor, even though, in fact, our function phi is close to 0. Because the function phi, so here, the function phi, what is it? It is, in fact, this quantity, which is square root of 3 here, divided by the distance between Q and all the remaining xi's, and these are large numbers because, in fact, I can make them as large as I wish by growing m. And so as you can see here, a Kd tree on such a point set would fail to separate the points, even though, in fact, even though I am dealing with an easy data set. And so this example shows that we are making a critical use of, in fact, random projection. So it's not just a mathematical tool. In fact, as usual in algorithms, randomization helps, right? It helps to actually get rid of complicated cases. Okay, so I think I'm going to stop here. And next time, so I'll be explaining you briefly. Of course, what we have seen so far is, I think, elementary algorithms which work well in practice and for which one can also say what the performances are. And so one natural question would be, okay, you have this function phi, but can you say something more precise about the function phi depending on the hypothesis which we have on the point set? Right? For example, if the point set lie on a hyperplane, on an affine flat of dimension k, or what if the point set is located on a k-dimensional manifold? Can we say something precise about the function phi? And so the answer is yes. So there are results which are precisely, in fact, giving bounds on the function phi, and from which actually one can bound the errors we talked about. And so this will close this section on refinements of Kd-trees, which again are simple, Kd-trees and random projection trees, which are simple, provably correct as a function of the intrinsic difficulty of the nearest neighbor search problem. Okay, thank you, and so see you next week.